Today we have a guest from HamSci, Gary McKeaton, and we're gonna go ahead and start with his presentation. Be courteous of his time since he drove in. So, Dave,
Yes.
do you have any more of an introduction before I hand over to Gary?
So, as Ralph said, tonight our guest is Gary, AF8A from HamSci, the Amateur Radio Community Activity Coordinator and a board member for HamSci. Gary, as I was writing the intro, it hit me that I think you're the first live celebrity we've had since COVID. Can anybody else think of anybody we've had in person? I can't either. Yeah, so tonight's a double treat. Not only do we have a live presentation, but we get to meet Gary in person and learn about HamSci. So Gary's biography information online says he has a degree from Case Western in electrical engineering and had a long career working for a major electric welding manufacturer. I could not find anywhere where he named who that manufacturer was, but for some reason, seeing he was up outside of Cleveland and such, the first thing that came to mind was that my first arc welder was a big red thing with the angled sides and a big knob on the front, and I'm thinking it might be the same company.
That was the AC 225, known as the Tombstone. Yes. 100,000 a year, those we used to sell.
So, several of us have been giving them the business over there because that's the CW corner of the room here. Gary is according to Bob, if he is heavy in the CW ops, and several of our folks have already introduced themselves, Rich, to it. So having said that, I think we'll just let Gary tell the rest of it. Please welcome Gary, AF8A.
Well, great. Thanks, everybody. Before I get into the formal presentation, I'll tell you the reason I wanted to drive down there from Cleveland was about 70 miles, a little over an hour. Just looking at your website, you all are active on the air. I saw the field day stuff. I saw the Ohio QSO party stuff. People that get on the low bands, I really enjoy seeing that. So that's why I figured, hey, it'd be great to meet you all and come on down here. All right. Tonight, again, thanks for having me at the MVARA. Today, I'll be talking about a collective called HamSci, the Ham Radio Science Citizen Investigation. I'll be talking about amateur radio, space physics, space weather, and how hams play an important role in HamSci's activities, and actually how each of you can participate in our current operating campaign. So my plan is the first part of my talk is to talk about HamSci a little bit. I'll open it up for questions, and then I'll continue on into, we'll talk about meteor scatter some more. So my introduction, you guys heard most of the details. Again, Gary McKeaton, my call sign Alpha Foxtrot 8 Alpha, which was randomly assigned, by the way, back in 1978. I've been licensed since my high school years, primarily operating on the HF bands. I started out as many teenagers, many of you did, probably in the late 70s, first as an SWL and a builder of Heath kits, and working my way up from novice to extra in my high school years. So my electrical engineering degree from Case Western Reserve, I put it to work in a 34-year career at Lincoln Electric. I was very fortunate to have retired a little bit early back in 2018. So now I can say that I am a full-time ham, no longer employed. My home station is pretty modest, so I tend to take my operating and contesting skills on the road. Speaking of the Ohio QSO party, the picture on the left here is with Goose, W8AV, when we were about to go mobile in the 2001 Ohio QSO party. In the middle, that's with Jim K8MR. We were going out in the Pennsylvania QSO party. And on the right, I was at the WWV 100th anniversary in Fort Collins, Colorado in 2019, which was a great event. But enough about me. We'll talk about HamSci a little bit. So HamSci was founded in 2016 by a soon-to-be professor, Dr. Nathaniel Fursell, W2NAF. It's not a formally defined organization. It's not an LLC, it's not a nonprofit, but just a loosely fit collaboration between members of the scientific community, many of which are university professors and ordinary, average, everyday ham radio operators. Hams play very vital roles as citizen scientists, volunteering, and we get to do what we enjoy, combining ham radio and this whole space physics, space weather thing. But that term I just used, citizen science, may be new to you. So let's go over that a little bit. If you look in the Oxford Dictionary, citizen science is scientific work. For example, collecting information that is done by ordinary people without special qualifications in order to help the work of scientists. So there are like dozens of citizen science projects out there utilizing volunteers with many different skills and interests. In fact, NASA is a big supporter of citizen science programs, providing both functional support and funding. So here's a few different examples of, including HamSci, we're one of NASA's official citizen science projects, and a link at the bottom if you wanted to learn a little bit more about citizen science. But at HamSci, we feel that hams are ideally suited to be citizen scientists because of our training and our technical abilities. And to be clear, there are no citizenship requirements when it comes to citizen science. All volunteers are welcome. So our HamSci sponsored activities, boy, there's a lot of stuff going on with HamSci today. In 10 years, the group has grown quite a bit. And there really isn't enough time to cover all the projects in detail. But I'll try to keep it at a high level and just do a few highlights here. I think the thing we're most proud of and probably best known for is something called the Personal Space Weather Station. It's hardware and software. The little stations that are hosted by hams all over the U.S. We've even got some all the way up in the Canadian North and one down at the South Pole. They're little receivers and signal processors that are used to study the HF spectrum, the shortwave bands. That's our biggest project. Basically, these receivers record WWV, WWVH, they decode whisper spots, FT8, and digitizing everything that's heard. Now, collecting data and digitizing it and storing it is pretty much meaningless unless you make it available to people who know how to use it, typically researchers. So a lot of time and effort has gone into the site that you see on the right hand of this picture here. It's our data collection system at the University of Alabama. That's where all these individual stations upload their data automatically every day. And as a researcher, you can go in there and download it and look at, say there was some solar flare that happened 6 months ago, and you wanted to look at everybody's shortwave response, you could do that. You could pull down the data from that time period. Another thing we're known for is our annual workshop. Science doesn't happen in a vacuum. It works best when people meet in person, exchange ideas, ask questions, and share what they know. HamSci has now sponsored 9 annual workshops. The latest, just in March, was co-sponsored by the American Radio Relay League and was held near league headquarters up in Connecticut. Our typical attendance is like 125 or so. But ham radio would be pretty dull without any operating activities. And HamSci has sponsored quite a few, many centered around the solar eclipses in 2017, 2023, and 2024. Those campaigns, while providing enjoyment and something to do as hams and do a little bit of contesting, had a very serious side as well. And that was generation and collection of data, such as reverse Beeson network, whisper, and FT8 spots, which again can be stored and then later analyzed. Those spots, I think, will be used someday to give a fairly clear picture of certain natural events, such as the eclipses, and later on we'll talk about meteor showers. If you do want to learn more about HamSci, the easiest thing, if you're a league member, is look in QST. They devoted a special issue to us last August, and just this month's QST, well, actually next month's, August, just came out a few days ago. We've got another special section in there with 14 or 15 pages, so you can dig in a little more deeply there. Lastly, I'll mention our website, hamsci.org. The collaboration between citizens and citizen scientists is clear throughout the website. It contains a lot of information talking about people, our projects, our research findings, details, agendas, and presentations from the workshops, papers, and a whole lot more. So that's my quick synopsis about HamSci, a group of professional researchers combined with citizen scientists, most of which are hams, studying the HF bands and primarily interested in what's going on in the ionosphere, but also the Earth's magnetosphere and some of the other good things that happen to come from the sun. So I'll break for a minute. Any particular questions about HamSci? Yes?
First one where the eclipse, and I've always wondered, what did you find out?
Okay, when we're done, I'll bring up some of the findings from that. And I'll be glad to show you that on the screen. It's a good thing. Good question. Yes, sir.
How do you get involved?
How do you get involved? The easiest thing is to go to our website. There's a little button there. It says Join HamSci. And that's the easy way is to get on our mailing list, which is a Google group. We've got about 1,500 people on there. But when you go to the website, there's also a Get Involved tab. And that Get Involved tab will talk about not only our various mailing lists, but also some of the Zoom conferences we have during the week. We have one centered around the Personal Space Weather Station. We have another one that we meet with the guys at Tapper. If you remember the packet radio craze back in the late 80s, Tapper is kind of our engineering arm, helping us design some of our equipment and that sort of thing. So start with the website, and that's a good place.
Thank you.
Good question. Okay. So let's start with one of our most current operating activities, since you guys seem to be an operating-oriented club. What this is going to talk about is meteor scatter communications, and we've got events almost monthly in 2026, so there's a lot of opportunities to learn and to jump in. Now, I realize that meteor scatter may sound like an exotic mode to some people, but I hope by the time I'm done, I can convince all of you that it's actually pretty easy to get on meteor scatter, to listen, and to actually make some QSOs. Pretty much anyone with an HF or VHF station, 10 meters, 6 meters, and whatnot. So today we'll start with some basics on meteors, and then we'll talk about how to use meteor trails as signal reflectors. We'll talk about the science we might achieve if the ham community joins us by operating and submitting data. And finally, a few words about the past and future runnings of our meteor scatter QSO parties. So meteors 101. Let's start with some basic definitions. So even if we're meteor scatter rookies, maybe we can talk about it a little bit and not sound like rookies. So there's three terms I want to cover. The first one is meteoroids. These are the bits in space. They're bits of matter thrown off most commonly by comets, but also by asteroids. They're bits of dirt, dust, and ice that's moving through our solar system, usually in a predictable orbit, following in the wake of their parent object. So just like we have planets rotating around the sun, we've got some of these asteroids and comets rotating throughout the solar system, and all their dirt and dust is following behind them. And I'll show you a little graphic of how that affects us. Now the actual term meteors, that's what we like as ham. Those are the bits of matter that as they're thrown off, they encounter the Earth's atmosphere at a high speed, burning up and eroding, often completely disappearing in just milliseconds. The last term is meteorites. These are the parts that actually make it to the ground. They're big enough to survive the reentry through the Earth's atmosphere. And if you're really lucky and you're a meteorite hunter, you'll find some of these things, put it in your pocket, and end up on the evening news, I guess. At least that's what happened back in March. So it can be a little bit difficult to visualize how meteors travel through our solar system. I mean, this is a 2D representation. It's colorful, pretty well detailed. It's a pretty good attempt. So those large rings, of course, are the planets orbiting the sun, and that cigar-shaped loop there, that is Halley's Comet. Halley's Comet was last year, in the late 80s or something like that. Right now, it's way out to the far right-hand side of it, but the trash and the dirt following behind Halley's Comet is still spinning around our solar system. That elongated path, that intersection is pretty important. It's a little bit hard to see here, but the other thing to know is that the plane of that comet's travel is actually tilted relative to our solar system. So if all of our planets are moving in a horizontal plane, this particular comet's plane of travel is tilted this way. When you get that tilt, you end up with an intersection twice a year between these bits of dirt behind the comet and our own atmosphere. So what happens there is you end up with 2 meteor showers per year thanks to Halley's Comet. Let's see. Yeah, those 2 showers are called the Orionids in October, and there's another shower called the Eta Aquarids that just happened back in May.
You're saying that meteor showers that you always hear about twice a year are all due to Halley's Comet?
Not all of them. Just these 2 are Halley's. there's a lot of other objects, and I've got a chart in a second that'll they'll spell those out. So good question. Guys asking the questions before I even got to the slides. You would think we had dinner and I fed them all these questions, but that's not the case. The dinner, yes, that was good. Okay, so right now you're all experts on meteors. Let's talk to the radio and ham radio aspects of all this. So meteors create signal paths. As I said, the physical process we care about most as hams is ionization, which occurs as meteors hurtle through our atmosphere, creating ion and free electron clouds, which are useful for reflecting radio signals over the horizon between a transmitter and a receiver, as you see up here in this picture. So these meteors scatter QSOs like this one shown here are typically in the 1,000 to 2,000 kilometer range. As anything else in nature, that varies a whole lot. But line of sight wouldn't work because of the curvature of the Earth. These aren't reflecting through the F layer or the E-skip or those other typical propagation methods. This is definitely an illustration of a meteor trail reflecting a signal. Just out of curiosity, it's kind of funny. We were at this HamSci workshop in March talking about meteors. A day or two later, I was home in Cleveland. Who else heard the sonic boom when the big meteor came across Lake Erie? I don't know if it was out in this part of the state or not, but you did. I know it shook our windows in my kitchen on the east side of Cleveland, that's for sure. So, so yep. And then all those folks were down there in Medina County looking for meteorites, or yeah, meteorites. So let's talk about operating meteor scatter a little bit. It doesn't take a real sophisticated station. You know, meteor scatter may sound exotic, but a simple station can make meteor scatter QSOs. 100 watts in an indoor dipole will actually work. But to be honest, 500 watts on a small beam, a Moxon, or even a high dipole would, of course, be a whole lot better. Personally, I used a 6-meter vertical and a 10-meter dipole, both in my garage attic, to enter the last couple of meteor scatter QSO parties as a listening station. I wasn't trying to transmit and have anybody pick up my itty-bitty weak signal, but at least I could receive other people doing meteor contacts and then contribute to the science, as I'll describe in a little bit. So I call this a quick start guide to making meteor scatter QSOs. I'm not going to go in a lot of detail about software and how to set it up, because if you're like me, you'll forget most of it before you get out the door. But I would like to point you in the right direction and at least make you comfortable with the idea of operating meteor scatter. So this is a couple of screens from the meteor scatter software, which is called WSJT. Anybody, and there's probably a lot of you in here that operate FT8, it's the exact same software package. In the lower left-hand corner, where you select between FT8 or FT4, one of the optional modes is MSK 144. MSK 144 is the mode that's used for meteor scatter. There's a lot of similarities when operating these modes. You've got the band activity window on the left. You can see your decodes. You've got the transmit message windows on the right for the things that are leaving your station. And of course, you've got the spectrogram at the top that gives you some idea of what's going on to in the audio that's being fed into your decoder. This software contains suggested frequencies. 50.260 on 6 meters is predefined, but there's a little bit of an oddity in that there is no 10-meter frequency for meteor scatter predefined in WSJT. I wish they would do that, but there's actually kind of a good reason for it. Up until a few years ago, it was illegal to actually operate this mode on 10 meters. The baud rate was too high. The data signaling rate was too high, and the FCC had for decades some rather archaic rules about what we couldn't do on the HF bands. Thankfully, they've changed those rules to a bandwidth limitation. As long as we keep our signals under 2.8 kilohertz wide, they're good. And MSK 144 meets that requirement. So now we can operate MSK 144 on 10 meters, and I'll get into it in a minute, but that's the basis of a lot of our science. But I've got some business cards here with QR codes in our website that explains a lot of the stuff, hamsci.org/MSQP. So my suggestion is, if this sounds interesting to you, is give it a try, because nothing ventured, nothing gained. My suggestion for meteor scatter rookies is to start by listening, especially on 6 meters where most of the activity's at, early in the morning. This is definitely an early birds mode. Many of the QSOs are made between 5 and 7 or 8 o'clock local time. So if you're up having your coffee and your better half is still asleep, You can turn on the radio and listen to some meteors. The other thing is there are some chat pages out on the web. The most famous, the best known of which is called pingjockey.com. It's a real low tech, but it's really useful in that as people are making QSOs and they talk about what they're hearing and where they're hearing them, and it might help you steer you in a little direction. I think if you watch some of the banter between the meteor scatter stations, I think you'll catch on pretty quickly. So there's one thing, a couple other things, I got a caveats I've got to give you too. So we've talked about meteorites. Got to beware of the meteor wrongs, as one of my buddies said. When these MSK 144 signals, again, this may seem obvious, but when we transmit a CQ and it leaves our antennas, we don't really have any control over the propagation mode that might bring that signal down to Earth and back to the receiver. That mode, if we're lucky, and we're looking for meteors, maybe MSK 144. But especially on 6 and also, of course, 10 meters, it may be good old F layer propagation that allows us to work DX all the time. Could be sporadic D or tropospheric enhancement or whatnot. So shown here is yet another mode. It's called aircraft scatter. You can see the little yellow dots. That's the reflected signals. They come back in kind of a picket fence because there's an airplane going by. And if somebody's transmitting their MSK 144, it's reflecting off the aircraft and coming down to the receiver. So this is not a meteor scatter QSO. It's the right mode, it's the right frequency, it's the right process, but an airplane got in the way. So now you can see, so some of the work of, as we talk about the science we're going to get into, one of the challenges is identifying all this data that comes in, which are the true meteor scatter QSOs, so we can set them aside and do science on them. And the rest of these guys, like aircraft scatter and F layer and so on and so forth, we set off to the side and maybe never use them, but you really got to differentiate between the two. And that's why we've got some smart people, one of which who just got her bachelor's in physics at the University of Scranton, using machine learning and artificial intelligence techniques to recognize these. So some poor guy doesn't have to open up thousands of these wave files and looking at them one by one and say, over here, over there, over here, over there. Let machine learning figure it out. So it's determining which mode these QSOs were made on is not an insurmountable problem, just one that has to be solved before we can delve more deeply into the science questions. Okay, meteor science is where I get excited. It's taking me now 23 slides to arrive kind of at the real purpose of my talk, to introduce you to and to excite you about the scientific inquiries that HamSci plans to undertake regarding meteor scatter communications, using data generated and collected by hams like us. So to begin with, what would science be without some equations? And these are some pretty detailed equations, so don't worry, I'm not going to go through them in detail or even superficially. But I realize it's kind of an eye test from out in the audience maybe, but especially if you're looking over Zoom, you can see in that left-hand equation, that's called, that equation was developed in 1961 by a gentleman by the name of McKinley, and it's the reflected power equation, or what I call the strength equation. Using all these factors of angles and wavelength and a whole bunch of other factors that are in here, it kind of predicts how much reflected power is going to come back. The key thing for us is this one term in here, lambda, which represents wavelength, okay? we've all studied wavelength, we all understand how that works in the ham radio world. In this case, the reflected power is actually proportional to the wavelength cubed. So when you move from 6 meters out to 10 meters in your wavelength, and this reflected power is mathematically related by the cube of that, that makes a huge difference theoretically moving from 6 meters to 10 meters. You should get far more reflected power, and I'll give you a couple examples of that. The right-hand equation is what McKinley came up with, called the duration, or what I call the length of the reflected signal. You send a radio signal up to if there's a meteor up there, it comes back. How long is that meteor able to reflect that signal? That's the length. And that's, again, McKinley came up with an equation for it. What he boiled the whole thing down to is the wavelength squared is really, really important. So these two equations, the strength and the length, are really affected by frequency or by wavelength. And that's the whole point of what we're trying to do here. So again, to repeat the equations, what I'd like to do is go through kind of a little bit of a thought experiment real quick. Let's see. So let me reiterate my statement earlier about stronger and longer and moving to 6 to 10 meters in a chart format, this little chart in the lower right-hand corner. And the center line is what if we could make a QSO on 6 meters on meteor scatter, 50.26. If we could arbitrarily assign a signal strength of 1 to it, right? Because all of our signal reports are arbitrary. You're 5 by 5, 5 by 4, 5 by 3. It's just kind of made up in our heads. We arbitrarily assign that to a signal strength of 1. And a relative duration, however long that reflection occurs, we call that a duration. We'll just set it to 1. We could make that exact same QSO. I know it's impossible. If we make that exact same contact with the same radio, the same power, the same coax loss, the same whatever, on 10 meters, in theory, according to the equations, the relative strength should be 5.69 times higher, almost 6 times stronger. The duration of that reflected signal, which you would see in that spectrogram at the top of the WSJT screen, should be about 3 times longer. So this is where the science comes into it now. So we've got some equations from 1961, before I was born, not by much, from 1961, stating how these things should work. So now we're saying to ourselves, okay, can we prove that those equations are right or are they wrong? And the way to do that is to get a lot of people operating on 6 meters and a lot of people operating on 10 meters and compare the results. What we really need are like thousands and thousands of QSOs on those 2 bands over a lot of different meteor events. Because the more data you've got, the more mathematics can be brought to bear in a problem, the more statistics can be used by people a lot smarter than me to look at these numbers and say, hey, you're right. The 10-meter signals really are 6 times stronger, or they really do last 3 times longer, or maybe it's all bunk. Maybe they're all the same length, and then these equations after 64 years will be, or 65 years will be proven wrong, and somebody will have to come up with new ones. But that's what science is. Sometimes you've got to, this may not be earth-shaking to a lot of us. It's not going to affect us. It's not going to put food on the table or gas in your car tank. But it's really interesting to understand how some of these things work and prove them right or prove them wrong. So we as hams, by making these QSOs and creating data, can help through that process. So how do we collect the data? Well, there's a couple of different ways in WSJT. One is really very simple, and in fact, it's almost automatic. And the other one takes a little bit of effort. So here's where we'll talk about ham radio meeting meteor science, data collection and utilization. So before everyone glazes over on the science part, we'll pivot back to ham radio a little bit. So this is one of the setup screens in WSJT-X. Most people, I don't know if they look at it or use it or not, but somewhere in the reporting tab, there's a little checkbox that says enable PSK reporter spotting. I think this is defaulted in the software. So whether you realize it or not, even if you're working FT8, as all those decodes are coming through your window, if you're connected to the internet, chances are those spots are being sent to a central server somewhere, the reverse beacon network, and it's storing them all. What it's storing is who the transmitting station was in your grid square, who the receiving station was in their grid square, what band, what frequency, and what time that those QSOs were made. There are millions of these records that are generated every day, because if you think about all the people sitting there watching FT8, watching the decode screens run by, the same thing will happen on MSK 144 if you're making meteor scatter QSOs or just listening. So if you enable this PSK reporter spotting, that helps a lot. The other part is a little bit more subtle. What I'd like to do is remind everyone that the so-called Joe Taylor digital modes, all the things you can do with WSJT, are all audio based. Your rig converts audio from your computer into RF and sends it down your coax and out to your antenna. When you're receiving something like FT8 or MSK 144, it's RF coming down your antenna, it's sampled or down converted by your radio and generally turned into your audio, often sent into a sound card, and then the software does the rest. Those audio signals are a gold mine for the researchers. And we are fortunate that the WSJT allows users to record all their decodes as .wav files, wave files, sound files. So when one of those meteor pings occur, if you're sitting there listening to the radio, you may hear one, it just goes, that's about all you hear, this little But that recording might tell us if that was a meteor scatter contact. It might tell us if it was aircraft scatter or F layer, E layer, or some other type of propagation. So it is possible in WSJT to set up to save just your decode signals as WAV files. And what we love people to do is at the end of these meteor scatter QSO parties, zip up their WAV files, upload them to HamSci so that the researchers can use this stuff and do their science on it. And the real value about that is hams all over the country. So there'll be people on the East Coast, people on the West Coast, people in between. We're mostly worried about the United States because that's where our funding comes from. But anyhow, on a worldwide basis. So it'd be great if everybody saved their decodes as WAV files and then uploaded them to HamSci. Yep. So what do we do with all this data? So earlier I mentioned, studying signal strengths and directions, strengths and lengths relative to wavelength, the McKinley assertions from 1961. There's also additional areas of interest, such as what about the echo ceiling height? Can we predict how high above the Earth or figure out how high above the Earth those echoes were taking place? Can we develop recommendations for station design, better frequencies, power levels, geographic footprints, antennas for more reliable meteor scatter operation? We don't know. If we get enough data, somebody may look at it and come up with some of those questions and help us as ham radio operators. You may open up the AR operating manual someday and find a chapter on meteor scatter written by somebody from HamSci that uses data to figure that whole thing out. So the other thing is, today we're fairly close to the peak of the solar cycle. So 10 meters has a decent amount of activity, especially in the winter. In 4 to 5 years, we're going to be at the bottom of another solar cycle, probably. If you want to operate 10 meters, this may be your best opportunity, especially if you're a 10 meter, if you like operating the 10 meter contest in December. I never knew this, but during the days when the band is dead and you can call CQ all you want and never get an answer, the good stations will actually move over to meteor scatter, try to make at least a couple contacts, add to their point total before the band opens back up and they can get on CW or sideband or whatever. So it's a lot of value to the whole thing. So we develop these ideas and we say, okay, we got to throw this out to the world so other people will participate. So what we do is we created a couple of what we call meteor scatter QSO parties. It's something we can write up information on our website, how to participate, how to save the data. We can go to magazines, websites, whatnot, with press releases and tell people what's going on. But the idea is hopefully get a lot of people on the air, a concentration of people on the air, more so than there would be on a normal day. We also went through a lot of effort this year to promote 10-meter operation, because most meteor scatter folks thought that was just never going to happen, or it didn't work, or it was still illegal or whatever. But we were pretty lucky. The results from our first 2 meteor scatter QSO parties from August and December last year had a reasonably good split between 6 and 10 meter operations. So we're starting to gather the data that people can analyze someplace in the future. Again, this is, I know this is hard to read. This is just a chart of the major meteor showers in 2026, and the last one's early 27. But these are when there should be enough meteors coming by that you can actually get on the radio, make a decent number of contacts as opposed to waiting an hour or two between contacts. Nobody wants to do that. These should come by at a reasonable clip. The next one is the Southern Delta Aquarids. That's happening at the end of July. And the parent object is whatever 96P Machholz is. I have no idea. I'm not an astronomer. But these are some of the actual parent objects that created these big clouds of dust that's moving around. We've got events all throughout the year. So to wrap up, I would like to acknowledge, when we get into these campaigns and have these ideas and do this research and stuff, sometimes you think it's just the ideas of a couple of scientists sitting in a corner somewhere doing whatever. But we actually, the idea for this meteor scatter stuff actually came from a young lady. Her name was Mackenzie, KO4GLN, who was actually interviewed not long ago on Kevin's video podcast, Q5 Amateur Radio. She's actually just finished her undergraduate nursing degree, but she's also a ham, enjoys participating with HamSci, and she says, we're done with these eclipses. We need to do something new. How about meteor scatter? And that's what this whole thing was born from her. One of the people that participates, Rob Suggs, He was just recently retired from NASA. He was the head of their meteorite office. Now we're talking about meteors as part of our hobby, right? But if you're in a space shuttle or a space station up there, meteors are a big deal. You want to get out of the way. If there's a big one that's going to come by, you want to get out of its way before it pierces your shell or whatever. And Rob was part of the team, ran the team that was supposed to make those predictions and help humans keep safe up in space. So, and there's also a team and an active community of HamSci folks that are participating. So the get involved question you asked me earlier, again, our website, our join HamSci button, join our Google group, and you can see all the other things that are available on our website. Our telecons, as I mentioned, there's the engineering telecom with Tapper on Monday nights. We talk about the personal space weather station on Thursday mornings. And on Thursday afternoons during the academic year, I host a Zoom session called Ham Science. We try to bring in a scientist who can speak on terms we can all understand about their research, astrophysics, how ham radio and their research interact, and so on and so forth. So that's kind of a learning opportunity on Thursday afternoons. I do also want to acknowledge, though I'm a volunteer and I'm not paid to do any of this stuff, I'm doing it because I got time on my hands. But the professional researchers, the students working on their graduate degrees and undergraduate degrees and stuff do need money. HamSci has garnered over $6 million in grants in the last 10 years. The National Science Foundation is a big supporter. NASA is a supporter, and ARDC, the folks that came up with 44net and have funded a lot of projects of many different types of the amateur radio community, help fund us. But specifically on the NSF and the NASA stuff, I want to say thank you to all you U.S. taxpayers, because we've all contributed to that through our tax dollars. And of course, all the people who maintain some of these other sites like WhisperNet and PSK Reporter and so on and so forth and whatnot. So we want to acknowledge all those people for helping us. So my parting words, I'd love it if some of you would join us in 2026, look into this meteor scatter thing, see if you might have any interest, and have some fun with it. That's the main thing. I will have some of our business cards here, again, with the QR codes, look just like this. I've got a couple of HamSci newsletters here. We had like 500, we took to Dayton. I've got a half dozen or so left. But if you're interested in HamSci at all, grab a newsletter, take it with you, and see what you can learn. So that's that. So that concludes my talk. So any questions on the topic? Yes.
Make it sure. So you said that everything goes through PSK Reporter, but then you said something about sending in WAV files. So what's the tie-in with that?
So there's two different kinds of data. So the PSK Reporter data will kind of give us an overall picture of where the QSOs were happening. But like I said, we can't be sure that just because you and I had a contact, what if we did it via aircraft scatter? That's really not germane to our meteor scatter study. So we need those WAV files. We can then find our QSO in those WAV files and look at the spectrogram and say, oh, that does look like a meteor blip. Let's set that aside and analyze it further. Or no, that thing looks like it was just the normal old everyday 10-meter propagation. We need to set that one aside. So one gives us kind of the gross overview of what's going on, and the WAV files give us the detail.
Does the ham send you the WAV files?
Yeah, unfortunately, it's a kind of a convoluted procedure, but yes, with the ideal thing, if you had 50 WAV files, collect them together, zip them into a zip package, and there's a website called Zenodo that is used for scientific data gathering. And you would create an account on Zenodo, upload your zip files, and that's it. Yes.
So, the meteor scatter QSO part. How does an operator know whether they're getting meteor scatter?
Well, the pictures are too hard to see on here. As an experienced operator, you would look at your spectrogram and you can recognize a meteor scatter ping, because the data burst that's sent out is only 72 milliseconds long. And it's a 15-second transmit window, much like FT8. And if you just see one little blip there that's really, really short, chances are that's one of those 72 millisecond things being reflected back to you. If that whole screen is lit up yellow, in other words, you had that those 72 millisecond packets are continuously being repeated back to you one after another, that tells me there's a different propagation mode effect. Because the meteor trails are so short, you usually get 70 or 100 milliseconds worth of data, and that's about it.
And so if I understood correctly, primarily 10 meters for that QSO frame?
Either 10 meters or 6 meters, either one is useful.
I'm trying to get a handle for how does somebody participate? And particularly coming in from the cold,
Sure.
how do they get up to speed on what they should be doing?
Yeah, that's why I said the thing to do now would be to, if maybe there's not a meteor shower going on right now, but get up early in the morning, start up WSJT, change it to MSK 144, and probably listen on 6 meters, the 50.260, I think it is. And you if you've got a 6 meter antenna that's a decent one, point it probably to the northeast from where we're at. And see if you start seeing some of these, you'll see your decode window light up with some decodes if some signals are coming back to you. That's the best way to do it, is to start as a listener. And then also at the same time, maybe open a window in your browser and join this pingjockey.net. And you may see a decode from W2CDH. Then you'll see a comment over in pingjockey.net from W2CDH saying, hey, I think I just made a QSO with so-and-so. And then you can start putting 2 and 2 together. Not required. It's helpful just because you're trying to pick a signal off of a meteor that's, 1,000 miles in the air. But people are successful with dipoles too. Yes.
When you have a meteor shower event, what kind of a time window would you have to work that? Days, hours?
Some of them are hours. It depends on the size of the cloud that meteor was from. I'm looking at that chart that I showed. It's really hard to see. There's an approximate rise and set time for the meteor showers that the NASA folks would publish. And most of those things, some of them are as little as 2 hours. Some of them are 12 or 15 hours. So if it's a really big cloud of dust coming through, some of those showers will have some staying power to them, but some won't. So there is an element of luck to this whole thing for sure.
We've been talking an awful lot about meteor showers. I sat through a really interesting, and I don't know if it's anything that you want to talk a great deal about, but I sat through a really interesting HamSci presentation 2 years ago at the Dayton Hamvention. There was a young lady that was talking about stuff out in the solar system, out in the universe, that HamSci was studying. Can you give us a little taste of that?
I'm trying to think who that might have been, because I was at Dayton a couple of years ago and I should have been in the forum. I might have been presenting. Most of our work involves, as I say, the ionosphere here on Earth. So we're typically not an extra outside the solar system and Milky Way type of research group. So most of our stuff is pretty well contained to what's going on in the Earth. Now, a lot of what we do is coming from the sun, obviously, but that's our own sun. Not so much other stars or nebulae and all those other wonderful astronomic things.
Cool. Thank you.
One more.
Balloon bounce, anything like that?
I have not, and HamSci hasn't done any work with that, but I really can appreciate the amount of effort and technology that goes into that sort of thing nowadays, but I certainly haven't.
So what has the data shown you so far? I know you did those eclipse studies. I participated in them with the eclipse and the meteor scatter. Has it shown that equation is fairly accurate in the meteor scatter? Or?
Well, we have not collected nearly enough data. Is trying to analyze those spectrographs and sort them out versus meteor versus non-meteor. The problem is, it's like any computer program. If you run it and you put one input into it and you get the right answer, you can't just walk away and say, I'm done. You've got to try, yeah, you've got to try it a lot of different ways. Put some big numbers in, put some small numbers in, put some imaginary numbers in, you know, whatever you, that, all that kind of stuff. So we need a whole lot more data before anybody can think about drawing conclusions, I think, on the meteor scatter stuff. The solar eclipse QSO parties, I'll try to bring some up on my laptop a little bit later. To make a long story short, we analyzed, not we, I mean, it wasn't me, but the science folks analyzed a lot of this RBN whisper data spots during the eclipses. And it was very obvious that 160 meters, for instance, was closed during the normal part of the day. But when the eclipse went by, most recently in 2024, between like 1500 and 1800 UTC, 6 meters, all of a sudden, excuse me, 160 meters, all of a sudden had a bunch of signals appearing. And 80 meters, the same thing. It was pretty much dead. Of course, it's dead because there's the D layers up there on a sunny day. It's absorbing the 80-meter signals so they can't propagate. But when the moon got between the sun and the earth, that D layer went away, and all of a sudden those 80-meter whisper signals could propagate. Similarly, 14 and 21 megahertz dipped down. The number of contacts being reported on whisper and the length, the distance between the stations on whisper changed significantly as the eclipse went by. One of the interesting things is there's what they call an asymmetry. These changes occurred at a certain rate. They had a kind of a curve to them. But on the back end, when the eclipse was fading away, they had a different curve. So for some reason, they happened quickly, but faded out very slowly. And that's one of the things the scientists are trying to figure out. And it's all pretty clear in the data, the people that know how to show this stuff. So I'll try to dig something up when I'm done and take a look. So, all right, that's it. Good. I'll see if I can dig some of the stuff locally. And thank you very much for having me tonight. And thank you for dinner. It was nice meeting you all.